Welcome to the session on Introduction to Multithreading. The topics covered are single-threaded software, multi-threaded software. In multi-threaded software, we discuss how to write a multi-threaded software and when to use multi-threading. We also move on to the shared data synchronization and discuss the concurrency. Finally, we summarize the topics covered and we see a lab on basic multithreading concepts. In a single-threaded software, each line of code is executed sequentially. The next line of code is blocked until the current line of code is being executed. At some instances, the software has to perform the multiple tasks at the same time. For example, writing a piece of code for a web server. It is required to handle multiple users at the single time, where the connection is accepted from the user and passed to spawn the process or to spawn the threads to continue the function. This facilitates the software to wait for another connection, and several clients can be handled simultaneously. The major difference between process and the thread is thread share memory, but process do not share memory. So how to write a multi-threaded software? Previous to C++11 standards, there was a requirement to utilize the operating system specific libraries in order to use the threading. For Windows operating system, it was the header file called windows.h. For Unix operating system, the header file is the Posix thread.h, due to which any software written on to be non-portable, which is meant that you have several guards or a conditional preprocessor code to make it portable. In the current scenario, that is the newer standards like C++17 standards, we use the standard template library threading features to write a multi-threaded software without worrying about the underlying operating system that is written for. The C++ standard template library gives us everything that we need to create threads, locks, condition variables, and mutexes. The C++ standard template library also provides the atomic variables, which provides a thread save and async functionality. So continuing with the multi-threaded software, the libraries used to create a multi-threaded software are atomic, which defines the different atomic wrapper types. The condition variables defines the condition variables. Thread defines the thread objects. Mutex define the mutex and the locking mechanism objects. And future defines the promise and the future objects. So all these will be discussed in detail in the coming sections. When to use multithreading? If a task can be broken into non-intersecting subtasks like divisible, mutually exclusive tasks, then threading can be employed in such cases. For example, searching the documents for data, encode many different music files, or download different files from the web. Multi-threading is useful during the asynchronous execution. During the simultaneous execution of the code, along with waiting for the occurrence of the external events. For example, pinging the remote server or drawing the graphics while also processing the user input. And also the second thing is distributing the processing across the multiple cores. For example, calculating pi to several digits. So in all these cases, we use multi-threading. In shared data synchronization, consider a case where two CPUs are trying to access the same data at the same time. If success, then they end up reading the same data in the global counter, else the inconsistent value is encountered. The local variable is becomes the global and global becomes the local. So the shared data between the two threads are like static int global is equal to 0. We encounter the condition where losing the interaction in the real time and the data is corrupted. And to avoid this, we switch over to the shared data synchronization. Continuing with shared data synchronization, consider two CPUs connected across a system bus. That is, CPU 1 and CPU 2 are connected across a system bus. A memory controller is connected to a system bus along with a random access memory. The memory controller is only in charge of making sure that memory and cache on a different processor stays consistent. If you write a memory on CPU 1, CPU 2 would not be able to read something else from its cache. So it is not the responsibility of the memory controller to make sure that they are both trying to manipulate the same data. There are few low-level instructions used to atomic operations and logging. These instructions are used at the operating system level to manipulate the small chunks of memory to create things like mutexes and semaphores. These are literally 1 or 2 bytes of memory they have that need to have the atomic or synchronized operations performed on them. Applications then build on top of this perform operations on the large data structures and resources. Continuing with the shared data synchronization, the multithreading is also used during the heavy CPU intensive processing or the distributed processing across the multiple cores. For example, calculating pi to several digits. And the task which is going to be faster is considered as the distributing the works across the separate CPU cores. For example, for one CPU, there are 6 cores, means effectively there are 6 processors that can run simultaneously at the same time. And each of these cores use the hyper-threading, meaning that each core can run 2 threads at any given time. That is 6 into 2, that is the 12 separate threads can be run at the same time. Dealing with concurrency, multitasking is a style of concurrent programming. Here, the applications which are implemented to launch a dynamic execution context at runtime are referred to as concurrent applications or the multitasking applications. The concurrent model of programming is required while implementing applications for any of the following objects. First is the event driven. So in event driven, the applications which need to respond to the various random events, for example, graphical user interfaces. The second model is the applications programmed for achieving scalability and the optimum utilization of the resources that is calculated in terms of the performance of the concurrent model. The various models of implementing support for the concurrent applications are the user level threading, which is many to one, and a kernel supported thread which is one-to-one. In user-level threading, as per this model, each dynamic context is initialized with a code and a stack segment and can share the rest of the segment of the address space from the parent process. Each user-level thread is identified and represented by a thread object, which is created and managed by the user-level application local process scheduler. Next is the kernel-supported thread, which is one-to-one. As per this model, each dynamic context is registered as a process with a kernel and it is assigned a address space. The kernel-supported thread is subcategorized into a process. It consists of address space and a process control block. And the second is the lightweight process, which consists of code, stack segment, process control block, and the rest is shared with the parent.